In this video, we continue our discussion of parameterizations of affine varieties with two examples. These are two examples that come straight from the book, but I think that they're really interesting examples. The first is a rational parametric representation of the unit circle, and the second one is dealing with the tangent surface of the twisted cubic. So we've got a unit circle right here. We know that when we're centered at the origin, the equation of a unit circle is x squared plus y squared equals 1. Now we're already familiar with one parameterization from trigonometry. And we know that if x equals cosine of t and y equals sine of t, well, I could square the x value and I could square the y value, and I'd get cosine squared plus sine squared is equal to 1. So as t increases, we know from trigonometry that we would just trace out this circle in the counterclockwise direction over and over and over again. Now we might be interested in having a different parameterization, like the rational parametric representation of the unit circle, because we might be interested in taking advantage of some of the properties of the field of rational functions. So we're going to use geometry to parameterize this unit circle in a different way using rational functions. And the approach that we use, I think, is pretty clever. Basically, what we do is we say, let's create a line segment from this location, x equals -1, y equals 0, to some other point on the circle. Now, if we are talking about a point over here in the first quadrant, calling that point xy, this line segment is going to intersect the y-axis at some y value between y equals 0 and y equals 1. We'll call that y value t. So for any point over here, I can draw a chord across the circle like this, and it's going to intersect the y-axis at a particular value between 0 and 1. So I draw a line segment like this, and it's going to cross there. And if I get closer to 1, it's going to cross there. If I get even closer to 1, it's going to cross there. But as t gets close to 0, it's going to cross or as t gets close to 0, the point xy is going to be over here. So as t takes on values between 0 and 1, we get all of these points on the other side of the circle if we look at that mapping. Now, if we drew a line segment, instead of drawing it from here to here, if we drew it from there to there, let's look at what that would look like. And I think I'm going to do all 4 quadrants. So I'm going to draw 4 circles here. Well, if I'm talking about a point xy in this quadrant, well, that t value is going to be some t value between -1 and 0, because if I take that line segment and I draw it over here, that t value is going to get closer to -1. If I'm interested in an xy that's closer to the x-axis, well, that t value is going to get closer to 0. But as t takes on different values between 0 or -1 and 0, you see if we keep drawing all of those line segments, starting from -1, 0 here down to this point over here, you see that for all of the points over here on this in this 4th quadrant, this line segment is going to cross the y-axis at some number between y equals -1 and y equals 0. So here, when we're in the first quadrant, t is between 0 and 1. And then over here, when we're in the 4th quadrant, t is between -1 and 0. And of course, if t is equal to 1, then we would be at this point right here. It would just cross here and here. So we wouldn't actually have 2 separate points. We would just, the point 0t and the point xy would be the same point in that case. But if we were starting at this point -1, 0, and we wanted to create a line segment from here to a point in the 3rd quadrant, Well, that will not cross the y-axis, not inside the circle. But if I extend that, it's going to cross at a y value down here. So if I'm continuing to think of this line as being the line of interest, now this goes through -1, 0. This point here would be labeled xy, and this point here would be labeled x equals 0, y equals t. So in quadrant 3, as I let this line segment start here at the very bottom of that unit circle, and then I let this point xy sort of go from here all the way up to here, the slope is going to change. That line is going to become steeper and steeper. The slope is going to become more and more negative. And as that slope becomes more and more negative, that t value is going to become smaller and smaller, larger in magnitude, but closer to negative infinity. It's going to be going down the y-axis. So here, t is going to be less than -1. And then, of course, if we were over here in quadrant 2, the same thing would happen. We would still cross the y-axis at a point 0t and the unit circle at a point xy, as well as this point x equals -1, y equals 0. But that chord would lie entirely in the circle. If we extend that line beyond that, beyond the circle, we see that that line will intersect the y-axis at a value of t that is greater than 1. This is quadrant 2. T is greater than 1. And of course, t equals 0, t equals -1, t equals 1. Those are all special cases. But I think you can see just from these 4 pictures that if I'm thinking about a line segment that starts at -1, 0, and passes through another point on the circle xy, that line segment will always cross the y-axis at some location, which we could denote by the point x equals 0, y equals t, because we have x equals 0, y equals t here, x equals 0, y equals t here. Even over here, if we extend that line, we have x equals 0, y equals t, and x equals 0, y equals t. With this in mind, and some very simple geometry, and just some knowledge of slope, we can find a relationship between x, y, and t that will allow us to come up with this rational parametric representation of the unit circle. Now, here's the key. Once we have decided to do this, and somebody was clever in deciding to do that, we could say, notice that the slope of this line segment and the slope of this line segment are exactly the same. Since they're exactly the same, we can set those two slopes equal to each other, and then we can write down the equation that relates x, y, and t to this point, -1, 0 as well. So I'm thinking of this particular location as x equals 0, y equals t. If I want the slope of this line segment, I just take the change in y and I divide by the change in x. So the change in y in this case is t minus 0, when the change in x is 0 minus a -1. And that has to equal the change in y over change in x on this line segment. Subtracting the y values, we have y minus 0 divided by the difference in the x values, x minus -1. And if we simplify that, that just gives us t equals y over x plus 1. So t can take on almost any value, but x has to range between -1 and 1, not including -1, because we can't substitute -1 down here. And that actually makes sense because we need 2 points on that line segment, not just a single point. X and xy can't be -1, 0 when we're looking at the slope of a point that also, or the slope of the line segment that goes through this point and this point. We can't use -1, 0 and -1, 0 here, made up of 0 over 0 form. So t is equal to this, clearly for x not equal to -1. And so that means we can rearrange that equation. We have y equals t times the quantity x plus 1. Now, if you're looking for a parametric representation of some curve, and that's what we're doing. We're looking for a rational parametric equation of this circle. We don't want y in terms of x and t. We really just want y in terms of t and x in terms of t. We want functions x of t and y of t that as t increases, we trace out that unit circle. So this isn't going to cut it. It's got too many variables in it on the right-hand side. But we know that x and y also have to satisfy this equation. So we can replace this y with t times the quantity x plus 1. And then I'm getting rid of y entirely. Then I have an equation involving x and t only, and then I can solve for x. And when I solve for x, yeah, that's great. Then I'll have x in terms of t. And once I have x in terms of t, I can substitute that in here, and then I can get y in terms of t. So that's the approach. We're making this choice, which is a clever choice, and then we're setting the slopes of these two line segments equal to each other, which would be exactly the same for any of these other pictures. And then we replace y with t times the quantity x plus 1 right here. So we have x squared plus y squared equals 1. And now we've got an equation involving x and t only, and we solve this equation for x. Now, if you're saying to yourself, how did you know to do that? I knew to do that because I was looking at a derivation in the textbook. The textbook suggested this method, but you can see what they're doing. They're just using something simple like slope and trying to find a relationship between some parameter and a general point on the curve xy. So you might be able to use this technique on other problems for other curves. But yeah, this is just an example of an approach that you could use in order to find those parametric equations. So now we've got this equation involving x and y and t right here. And then we use it to solve for y. And then once we have y in terms of x and t, we substitute there. And now we have x, an equation involving x and t only. So now let's solve for x in terms of t. You can do that this way. Excuse me, we have a product squared, so we square the first factor and square the second factor. Now, we want to solve this equation for x in terms of t. Now, this is quadratic in x. It might not be obvious it's quadratic in x, but if you think of t as a fixed value, so t has some particular value, this is x squared plus a constant times the quantity x plus 1 squared, which is x squared plus 2x plus 1 if we FOIL, and that equals 1. So this is quadratic in x, and this is quadratic in x, and you can almost think of this as a constant. So this is a quadratic equation in x. In general, this would have two solutions, or up to two solutions. If I want to solve this quadratic equation in x, I might try subtracting 1 from both sides and then factoring, or using the quadratic formula. That would get you to the same answer as well. But I'm going to try something a little different. Rather than distributing here and collecting like terms in x and then using the quadratic formula in order to get x by itself, what I would like to do is I'd like to subtract 1 from both sides, but when I do that, I'm going to subtract it and I'm going to put that -1 on the left-hand side in a very specific location. I'm going to group that -1 with this x squared minus 1 over here, which is legal because we can group in any way we want. That's the associative property of addition of real numbers. And the reason why I'm making that choice is so that this is easier to solve, this resulting quadratic equation. Now, if you're saying that doesn't look easier to solve yet, remember this x squared minus 1 can be factored. That's a difference of squares. That's x plus 1 times x minus 1. And now I can just use factoring by grouping, sort of high school algebra stuff, in order to factor this. I can look at this group and I can ask myself, well, what do these two groups have in common? They both have an x plus 1 in common, so let's factor that out. And then we ask ourselves, x plus 1 times what gives us this? Well, I have x plus 1 times x minus 1. That gives us that expression. And then we ask ourselves the same question, x plus 1 times what will give us this? Well, I need a t squared. This has an x plus 1 squared. I factored out one of them, so I should still have one left. And so we're here. Now we have this times this equals 0. Okay, so if I have this times this equals 0, and remember, x is not equal to -1. Since x is not equal to -1, that means this is not 0, so that means that this must be 0. And I think I'll distribute that t squared now. So since x is not equal to -1, you can add the 1 to both sides, and you have x plus 1 is not equal to 0. And now you have this equation that you can solve for x in terms of t. It's easy enough to do. Just group the terms involving x. I've got one here and one here. And then I've got a t squared and a 1. I think I'll add that 1 to both sides and subtract that t squared from both sides. And then let's factor out the x over here. It's just pre-calculus stuff. You get all the x's on one side, everything else that does not involve x on the other side. Factor out the x. And if you're trying to get x by itself, you divide. So now we have a parametric equation for x. X is 1 minus t squared over 1 plus t squared. When x equals 1 minus t squared over 1 plus t squared, and t takes on a range of values between -infinity and infinity, I claim that we get all of the points on this circle except for that one, except for -1, 0. Because this point xy was based on the assumption, or this equation involving xy and t was based on the assumption that xy was a different point on the circle from this one, -1, 0. So we have this for our x value. Now, if we want our y value, it's actually easy enough to do. You already know what y is in terms of t and x. So now you can replace x with this expression here. So y is t times x plus 1. And x is 1 minus t squared over 1 plus t squared. In order to simplify this, I would get a common denominator. The common denominator is 1 plus t squared. And then since the denominators are the same, you can add the numerators. You have 1 minus t squared plus 1 plus t squared. The t squared and the negative t squared reduce, and then we just end up with a 2 in the numerator over 1 plus t squared times t over 1. So we get 2t over 1 plus t squared. Oops, there we go. So now we have these parametric equations representing the unit circle. X of t equals 1 minus t squared over 1 plus t squared, and y of t equals 2t over 1 plus t squared. And I'm not going to prove it to you. I think I proved it to you in a different video. But if I take the x and I square it, and I take the y and I square it, and I add them together, I claim that I get 1. So all of the points that satisfy these two equations at the same time also satisfy the equation of that affine variety. So remember, this corresponds, that curve, actually, let me just label this first. These are the rational, or this is a rational parametric representation of x squared plus y squared equals 1. And remember, x squared plus y squared equals 1, that's an affine variety. It's typically represented this way. It's the variety defined by the polynomial equation in two variables, x squared plus y squared minus 1. This is a set of all points x, y, such that x squared plus y squared minus 1 equals 0. And if we add the 1 to both sides, we get this. Now, this is the entire circle. That's the variety. Now, the rational parametric representation is this. Every single point in the rational parametric representation lies on the variety V, or in the variety V. But there is a point in V that is not in the rational parametric representation. That's true in general. So let's write that down. Every point of the parameterization lies in V. So the mapping that's given by this only returns values that are in this circle V, but there may be points in V that are not mapped by that parametric representation. And I'm going to say not given by a particular t value in the parametric representation. So I just thought that was kind of cool. That's how we come up with that. And it was clever. Someone said, let's take a chord like this, set the slopes equal to each other. That gives us a relationship between x, y, and t. And then let's make a substitution and solve for x. And then once we solve for x, we can easily solve for y. And then we have this rational parametric representation, which might be particularly useful because of the properties of that field of rational functions. Now we also want to look at another use of geometry to parameterize affine varieties, and that's going to yield what's called the tangent surface of the twisted cubic. Now remember what the twisted cubic is. Now, the twisted cubic is a variety V defined by the polynomial functions y minus x squared and z minus x cubed. So those are polynomials in 3 variables. So this is the set of ordered triples x, y, and z in 3-dimensional space such that y minus x squared is equal to 0 and z minus x cubed is equal to 0. And of course, we could add x squared and x cubed to both sides of those equations respectively. So we have y equals x squared and z equals x cubed. Now this is a parabola in the xy plane. But z is free to be anything, so we're going to see that parabola again for different values of z. So that is the best sketch I can give you for y equals x squared. That's a cylindrical surface. It's a cylinder in the multivariable calculus sense. The rulings are parallel to the z-axis. It just looks like y equals x squared, but then z is free to be anything, and so it extends in the z direction. It would extend up and down. I'm just drawing part of it above the xy plane there. Now this is very similar. This is also a cylinder. Now if I take this right-handed coordinate system where my z-axis is going up like this and my x-axis is pointing straight out at us, my y-axis would actually be over here. But if I rotate that like this, the z-axis would be pointing straight up, and my x-axis would be pointing to the right or pointing to the left instead of pointing to the right. So if I want to graph z equals x cubed, it's going to look like this. It's kind of like negative x cubed from your pre-calculus class, but that's just because the positive x-axis is over here rather than here. And we're putting the positive x-axis on this side because of where it is relative to z over here. Like you can imagine taking this and shifting it like this, and that's what you would see. So this z equals x cubed looks like this in the xz plane, but remember y is free to be anything. So the y-axis is pointing straight out at us like this, and this surface kind of look like this. It's like a cubic function coming out of the page, coming out straight at you. If I try to draw it, and I will try to draw it, it's not the best. Here's the z-axis, here's the x-axis. We're going to see a cubic function over here, and then on the other side of the xz plane, you're going to see a cubic, like the rest of that cubic over there. You have to imagine that that's behind the yz plane. But this is the same. We're going to see this cubic function. It's going to look the same no matter what y is. So we'd end up with a surface that kind of looks like this, and then it goes back behind the yz plane, like that. Again, it's not a great graph. But this twisted cubic is the curve of intersection of this cylinder and this cubic cylinder. This is parabolic cylinder, and this is a cubic cylinder. Let's graph this on CalcPlot 3D. So right now I have y equals x squared graphed up here. So you can tell when you look at this from above that that's y equals x squared. The z-axis is going straight up. So y is equal to x squared and z is free to be anything, so we get that. Or if we want x to be equal to z, or z to be equal to x cubed, excuse me, and y to be free to be anything, we see that. That's what I was trying to graph on my paper. That's what that's supposed to be. Now, let's graph both of these at the same time. Oops, that was not my intention. And let's use 60 grid lines. And then let's go to y equals a function of x and z. Let's use x squared. And let's use 60 grid lines here as well. The twisted cubic is where those two surfaces intersect. So you can see that it's a cubic function because it lies on this z equals x cubed, but it's twisted because you're looking at where z equals x cubed meets this parabolic cylinder. So there's part of the twisted cubic. And there's another part back there, and another part over there. I hope you can see all of that together. Now, coming up with a parametric representation for the twisted cubic is actually pretty easy. Remember what we talked about earlier when we discussed dimensionality. This is an affine variety in three-dimensional affine space where our field is the field of real numbers. And it's defined by two equations. We generally expect the dimension of the affine variety to go down by 1, starting with the number of dimensions from affine space for each equation. So if I have one equation and I'm looking at an affine variety in three-dimensional space, I expect it to be a surface, and that's exactly what we get. With this one surface, this one equation in three-dimensional space, we get a two-dimensional object, which is a surface. But if I have one surface here and another surface here, the two surfaces together, well, that's adding, this second surface is adding an additional constraint. So this is reducing the dimension by 1, gives us a surface, and this is reducing the dimension by 1 more. which gives us a curve. And we were just looking at that curve in three-dimensional space where this guy and this guy intersect. Now, a curve is one-dimensional in the sense that it can be described by parametric equations involving one variable only. Since we already have y in terms of x and z in terms of x, we can just let x equal t. That would be our parameter. And then as long as y is equal to x squared, which would be t squared in this case, and z is equal to x cubed, which would be t cubed in that case, we're going to get parametric equations that satisfy this and this at the same time. And as t takes on a range of values, we're going to trace out that twisted cubic in three-dimensional space. So these are the parametric representation or parametric equations of the twisted cubic. And of course, the twisted cubic is an example of an affine variety in three-dimensional space. So this is it is a rational parametric representation of the twisted cubic, but since these are all polynomials in T, we can think of it as a polynomial parametric representation of the twisted cubic. And we kind of already know what this looks like because we were looking at where this guy intersected with this guy, but I'd like to see it without all of the surfaces sort of blocking our view. So let's look at this in CalcPlot 3D using the capabilities of CalcPlot 3D to graph a space curve. Now, if you've had Calculus 3, you know that we can graph space curves in this way. In Calculus 3, we used this notation. R of t is a vector valued function with components x of t, y of t, and z of t. Now, in some books, rather than using these braces on the side like this, we use this alternate notation. It looks more like a point, x of t, y of t, z of t. We use parentheses, a parent on each side. That is the notation that is used by the author of, or the authors of the algebraic geometry textbook that we're working through right now. So if we want to graph this, we're thinking of r of t as being given by parametric equations t, t squared, and t cubed. So let's do that in CalcPlot 3D. Okay, so we've got y equals x squared over here and z equals x cubed back here. And we know that the curve of intersection is right here. And we're calling that a twisted cubic. It looks like a cubic function, but it's twisted because we're looking at where a cubic function intersects with that parabolic surface, that parabolic cylinder. Rather than looking at it this way, let's look at it without the distraction of the two surfaces. Here I want to graph a space curve. So I choose space curve from my list, r of t, and it gives you sort of a generic space curve to start. It gives you a helix. Let's delete the equations of those components. We want x to equal t when y equals t squared and z equals t cubed. If we let t go from -10 to 10, we get something that looks like that. Now you might think that doesn't look like a cubic function at all, but it is cubic in terms of x and z, but it's twisted because it's intersecting that parabolic cylinder given by y equals x squared. So you can kind of see the cubic function there, but you can also see the parabola if you look at it from the appropriate angle. Oops, there we go. So as I go closer to the y-axis, you can see that cubic because z is equal to x cubed. But if I look at it from above, so from the positive z-axis, you can see that parabola, that y equals x squared. And that's our twisted cubic. Now, if you want to see that alongside those surfaces, oops. So let's use a constant primary color. We can graph that with this surface here. And you see that that twisted cubic intersects with this surface. Now, if you're saying to yourself, that's not perfect, it should line up with that surface, you're right. It's just because I'm letting my x values go from -2 to 2, my y values go from -2 to 2. If we had taken a wider range of values here, it should match. This curve should lie on that surface the whole time. Let's also graph y equals x squared, and I want 60 grid lines. And so now you can see where y equals x squared intersects with z equals x cubed, and then we have this equation here. I like it in the royal blue instead. But let's get rid of the surfaces again. And now we've got our twisted cubic. Now, that was pretty easy. It's easy to come up with this parametric representation of the curve of intersection of this and this, because we know each equation reduces the dimension by 1, and so 3 minus 2 is going to give us a one-dimensional object, and that one-dimensional parametric representation looks like this. Well, if I'm on a particular curve at a particular location, at that particular location, I can find what's called the tangent line. If we look at all of the tangent lines together for a particular curve, that's what's called the tangent surface of that curve. Let me write that down. So we're going to find and graph all of the tangent lines. To a curve. That set of all of the tangent lines to that curve is called the tangent surface of the curve. And this is how it works. So let's say you've got some curve and it looks like this, and you're at a particular, and it's given by r of t with components x of t, y of t, and z of t. At a particular value of t, you would be at a particular location. So this might be x of t naught, y of t naught, and z of t naught. Well, the tangent line here is given by, or excuse me, the direction vector of the tangent line is given by just the derivative of this thing. We know that the tangent vector to r of t is just r prime of t. So if I try to sketch my tangent line, and we're just kind of eyeballing it here. That's my tangent line. The tangent vector should be given by r prime evaluated at t naught. So that's r of t naught, r prime of t naught, which is given by x prime of t naught, y prime of t naught, z prime of t naught. Now, if we want the entire curve, we have to take that tangent vector and we have to multiply it by a scalar. If we multiply it by 1, we're going to go from here to here. Well, if we multiply it by 1 and then we add that result to this, the vector that points to this location, that's going to get us from here to another point. If we multiply by 2, it's going to get us just like a distance of 2 of those lengths of the vector away from this initial point. We multiply by 3, we're going to be 3 units away from that initial point, and where a unit is given by the length of that velocity vector evaluated at t naught. So this tangent line can be easily found just using what we know about lines from multivariable calculus. Now, this is from multivariable calc, so if you don't remember, or if you've never had Calc 3, then I'll just explain it to you. If we have a line that passes through the point x naught, y naught, z naught, and that line has a direction vector v given by components a, b, and c, it turns out that the parametric equations are x equals x naught, y naught, or x, y, and z start at x naught, y naught, and z naught. And then we add some parameter t times the components in the x, y, and z direction. So we're going to have an AT here, a BT there, and a CT there. When t equals 1, we go from x naught, y naught, z naught to x naught plus a, y naught plus a, or x naught plus a, y naught plus b, and z naught plus c. When t equals 2, we'd end up over here, and so on. If t equals -1, we'd end up on the other side. That's exactly what we're doing over here. Now, the problem is we've already used t for another purpose. The t value is designating a particular point on this curve given by r of t. So we're going to need another parameter. Rather than using t to trace out the rest of this line, we need another parameter. The textbook authors for the book that I'm using call that parameter that traces out the rest of this line u. Excuse me. So the parameter u gives a particular location on the tangent line from that point of tangency. And the parameter t gives us a particular location on this curve. Or if we're talking about fixing t for a second, the parameter, well, let's say the parameter t identifies a particular location on the curve. So if I want to come up with the equation of this tangent line, well, actually, let's just come up with the parametric equations for the tangent line. I would need my x, y, and z to be functions of the parameter u. As u increases, we trace out this side of the line. As u decreases, when u is a negative number, we go this way. And we start at a particular location, and that initial location is x of t naught, y of t naught, z of t naught. So this is the tangent line to the curve given by r of t at t naught, or at the location given by t equals t naught. And then the velocity vector at here that is represented over here by the direction vector with components a, b, and c has components x prime of t naught, y prime of t naught, and z prime of t naught. And we take each of those components and multiply by u, and then we add them to that initial location to get the entire curve. So this looks a little different than this, but it's exactly the same thing. Instead of x naught, y naught, and z naught, we have x of t naught, y of t naught, and z of t naught. And instead of a, b, and c, we have x prime of t naught, y prime of t naught, and z prime of t naught. And then we have a u there. And as u takes on different values, we're on this curve in this way. But here's the key with the tangent surface. We don't want just a particular tangent line. This is a particular tangent line at t equals t naught. We want all of the tangent lines. So we don't want to fix t naught. We want t naught to take on any value t in the domain of the original vector valued function r of t. So the tangent surface has parametric equations that depend on two variables, u and t. So we'll have an x of t here, a y of t here, and a z of t here, and then an x prime of t, and a y prime of t, and a z prime of t. Now, if you're having trouble wrapping your mind around this, you might pick a particular value of t naught and a particular r of t and actually work this out. So let's see if our r of t is given by the parametric equations of our twisted cubic. So we have t, t squared, and t cubed. R prime is a vector with components 1, 2t, and 3t squared. Now at t equals 1, we would be at the location 1, 1, 1. So we'd have x of u, y of u, and z of u for the tangent line. Well, that tangent line would pass through the point 1, 1, 1. That's our x naught, y naught, z naught, or x naught, y naught, z naught there. And the slope at t equals 1, or the direction vector at t equals 1, which indicates like the slope in three-dimensional space, would be given by this vector evaluated at t equals 1. So we'd have 1, 2, 3 there. That's our A, B, and C. And then we take all of those and we multiply them by this parameter, and we're using u instead of t because we want to leave t for something else. And we have this now. So these are the parametric equations of the tangent line to the twisted cubic at the location at the location 1, 1, 1. So let's look at that. Now, when I type my parametric equations into, I type the parametric equations of this line into calcplot3D, they're going to ask for these to be functions of t and these to be functions of t. That's totally fine. Just remember these t values are indicating locations on the twisted cubic, and these t values are giving us locations on a tangent line. That's totally fine. It's like one function of x and a different function of x. Okay, so we still have our twisted cubic right here. Now let's graph another space curve. And we want to use the parametric equations of the tangent line at 1, 1, 1. So x is given by 1 plus 1 times the parameter, which is just t, because they're asking us to use t rather than u. Then we're going to have 1 plus 2 times the parameter for our y value, and 1 plus 3 times the parameter for our z value. Let's graph that. And do you see that it passes through 1, 1, 1? I hope that you do. X equals 1, y equals 1, z equals 1. Rather than letting t go from 0 to 2 pi, let's let t go from -10 to 10. I hope that you can see that that is tangent to the curve at 1, 1, 1. It's a little bit hard to see. It is hard to see. There's 1, 1, 1 a little bit. It's tangent to the curve at 1, 1, 1. Yeah, so that's just our first one. Okay, that wasn't very helpful. That's okay. So that's, but you could see the point of tangency at 1, 1, 1, and maybe you said, I don't really know if it's tangent. It's a little bit difficult to see. Now that's for a particular location. Now here we're talking about an entire tangent surface, a surface that's defined by these parametric equations. So we're going to do the same thing that we did here, but instead of plugging in a particular value of t, we're going to let t vary. T can be anything. So We have x of t, y of t, and z of t, which are given by t, t squared, and t cubed. And then we're adding our parameter u times x prime, y prime, and z prime, which have components of, or x prime, y prime, and z prime are 1, 2t, and 3t squared. So the tangent surface is given by these functions after some simplification. Different t values give us particular locations, points of tangency on the twisted cubic. Different u values sort of take us away from that twisted cubic and take us off to other points on that tangent line. So let's see how that works when we graph it in CalcPlot 3D. Okay, so we've got our twisted cubic right here, given by the parametric equations t squared, or t squared and t cubed, respectively, for x, y, and z. Now, if we want to graph a parametric surface, go to this drop-down list and look for parametric surface. It's right there. Now, they're using the parameters u and v rather than u and t, and that's fine with us, because we know these variables are just dummy variables. And I've got my equation of my tangent surface right here. X is equal to t plus u. So I'll use v for t. So I have v plus u. And then I have v squared plus 2u times v for y. And then v cubed plus 3 v squared times u for z. And they have a range of values where u goes from negative, or from 0 to 2 pi, and v goes from 0 to pi. I don't really want 0 to pi. I want, well, this is a range of t values that goes from negative 10 to 10. So, and our v is playing the role of t here. So I want v to go from negative 10 to 10 as well. Maybe let's take 30 steps. And let's just let u take on a very small range of values. Let's go from 0.5 to 0.5 so that we can see the tangency. You see that that's tangent to the curve? Gives us the surface. I think it's pretty cool. Now, if we want to see it a little bit better, let's let u go over a larger range of values, negative 1 to 1. Oh, hello. That blew up pretty quickly. But this is our tangent surface. It's kind of cool. And if we wanted better pictures, I guess we could take more steps. Let's do 60 here and 60 here. See if it can handle it. It's a nicer picture. I'm not really sure what's going on there. Sort of twisting on itself. It's easier to see what was going on when we let u take on a smaller range of values. And I got it sort of rotating, and it's not going to stop. There we go. But you see that tangent surface to the twisted cubic, and now even with this tangent surface on it, it's a little bit more obvious that it's a cubic function that has been twisted some. Okay, so that is an interesting way that we can use geometry to come up with a tangent surface to some curve, and that curve was actually an affine variety as well. So this may define an affine variety. We've got these parametric equations involving u and t, and there might be a question like, okay, if we've got a tangent surface here, and we know it's related to the affine variety, given by these two polynomial functions, y minus x squared and z minus x cubed. The question might be, is the tangent surface itself an affine variety? Or in other words, is there some equation out there a polynomial function, f of x, y, z, in this ring of polynomials with real coefficients in the variables x, y, and z, such that f of x, y, and z equals 0 when x is equal to x of this u and t, and y is equal to this y of u and t, and z is equal to z of u and t, these three parametric equations of our tangent surface. Or in other words, if this is a parametric representation of the tangent surface, and we see that it's a polynomial parametric representation because these are polynomials in the variables u and t. This question is asking, in other words, is there an implicit representation? And remember what we said last time. Yes, there is. If we have the parametric representation of some affine variety, we can come up with the implicit representation. And doing that would involve taking these equations for x, y, and z and manipulating them in such a way that we get rid of the t and we get rid of the u, and we just have an equation involving x, y, and z only. So it's somehow going from this to this. Now there is an algorithm for that. So we do have an algorithm to find this polynomial function f of x, y, and z, so that f of x, y, and z is 0 when these parametric equations are satisfied. And that algorithm is discussed in chapters 2 and 3. Now, it turns out that that function, f of x, y, and z, is this. It's negative 4x cubed times z plus 3x squared times y squared minus 4y cubed plus 6 times x times y times z minus z squared equals 0. This is your function of x, y, and z. So this is a parametric representation of that surface, and that surface can be thought of as the affine variety defined by this function. And if you're saying to yourself, how on earth did they get that? That's what this is for. This is a teaser. It's saying we can get that using the algorithms discussed in chapters 2 and 3. And now if you're also, again, wondering, what does this mean that this and this give you the same surface? That just means if you replace x with t plus u, and you replace y with t squared plus 2 ut, and you replace z with this function, and you substitute those into this equation, and you do all the algebra and you simplify, guess what? Everything's going to cancel out and you're going to get 0. So when x, y, and z satisfy these equations, you can plug those x, y's, and z values or expressions for x, y, and z into this equation, and you're going to get the right thing. You're going to get 0. So that is the end of our discussion of those two examples. Next time, we'll talk a little bit about an example from computer-aided geometric design.